Howdy. We should be recording now. I apologize for all the rain. I've got my noise canceling going maximum power. Here we go. NVIDIA RTX voice. We'll give that a shot. I've been using it. I seem to like it. It's not too bad for free. So waited all day on the rain to stop. Just wouldn't do it. We're ready. I'm gonna try and speak up. Still trying to get well. But we're going to cover naming compounds, and I'm going to do it for both courses that are going to be using this right away. We've got the fundamental chemistry book and the general chemistry book. We cover them in chapter 3 in Fun Chem and chapter 2, the end of chapter 2 in general chemistry. And the only real difference between the two is, other than page numbers, is how the Gen Chem doesn't quite go into electronegativity yet. So if you hear me throw that term and you're not quite sure, we'll cover that, some basics on that. And it mostly relies on us knowing a metal, for being a metal and a non-metal, to know things are ionic. So we'll cover this. We did a lot of this in class. So I'm going to start off by looking at the two tables that I recommend that you learn. So we'll start here in the fundamental book, and it is, there we go, page 96. I've got table 3.3, and it has our list of polyatomic cations and anions. The ones I want you to know are the ones in red. All right, so this is a pretty good table. It's got it says the most of the common ones, but the most common ones are in red. And so I want you to know in the name, the formula, and the charge. If it was me, I would work this out as a series of flashcards. And so I might put ammonium. All right, and then see if I can write it a little bigger. NH4 with a positive on the back. Now, why I recommend flashcards? A lot of you have apps that you use on the phone. That works as well too. But you're not going to want to carry your book around, especially now that it's all electronic anyway. And you're not going to want to carry your notes around. But flashcards you can throw in your pocket, throw in your purse, and you got them at work. Pull them out. You're just not going to get in trouble for that. Whereas pulling your book out, hey, what are you doing? All right. I like them because if I'm sitting there waiting on in between classes, I can flip through them. I can quiz other students in lab. It's a great way to practice. And then even if I were to give you this list, I would still want you being familiar with these and knowing them, because we're going to see these polyatomic ions so often. And we'll talk more about what they are and how to do things with them, but we will use them so often that you need to get used to seeing them as one solid piece. Now, flip over here to Gen Chem. The Gen Chem, it's on table 2.5, and it is located, don't you love my bookmarks? There we go. Quality education. All right, so table 2.5 is on page 58, if I can read that correctly. And again, same kind of idea. You want to know the name and the charge and the formula. So this one has quite a bit more. Again, even if I give you this, you're best served overviewing these and practicing these, so that as we move further on, or if you see a name, you immediately think polyatomic ion. And we'll actually cover quite a few of these. And then we'll also be worried about some of the oxygen-containing ones. So we see nitrate, nitrite, sulfite, sulfate. We'll cover those as well. It's an older system, but Gen Chem is required to use it. So I'm going to cover that today as well. So the next page I'll go ahead and look at in Gen Chem. It is on table 2.6 on page 60. And it's our prefixes 1 through 10 that we use for our covalent systems. All right. In fundamental chemistry, that should be on page 99, if I remember correctly. Yeah, 99, 3.4. Same 10 prefixes: mono, di, tri, tetra, penta, hexa, hepta, octa, nona, deca. And you're going to practice those the same way you practiced counting when you were a kid, and the same way you would do in a foreign language. So you want to get used to hearing these, to saying them, and to associating them with words. And there is no shame in using your fingers. All right, so mono, di, tri, tetra, penta, hexa, hepta, octa, nona, deca. And some of these you probably have heard or used before. They're pretty common prefixes, but you got to know those prefixes 1 through 10. All right. You will hear them, you will use them. So might as well just go ahead and make a point out of learning it. So let's start with our naming overview. Our naming overview here. This is the hardest part of doing any naming kind of lecture and any kind of naming practice. If my head is tilted, or I know the RV may be tilted one way, and I think the camera's tilted the other, and the monitor seems to be somehow tilted a third. I don't know. I think I need some more cough medicine. My wife got into my cough medicine stash and cleaned me out. I have to run through the county line and pick up some more. All right, so naming overview. The hardest part on this and all of these naming things is deciding which system to use. So here's a brief overview of these naming systems that are still commonly in use. So we've got standard binary system for ionic things. This will be things with group 1, group 2, and aluminum. Then we've got our polyatomic ions we were just discussing. We'll talk about those a bit more. The IC and the US system and the stock system, those are both used when we're dealing with the transition elements and under the staircase except aluminum. And then down here I've got common naming, and you'll notice it's on both covalent and ionic. And the common names, there's a list of those that I should give you, and I want you to know, but there's a lot of other things that have common names. Matter of fact, if I go pick over there, I've got ibuprofen. And so that it says generic for, so it says generic for Advil or whatever, right? Compared to Advil. And so when I look at this, though, the actual chemical compound in here for the main ingredient for ibuprofen, this is a trade name. All right, it's a common name. So there's lots of common names that we use. Many of them rely on old systems that were based purely on memorization, and we'll see some of those. Where now at this point we just memorize the answer instead of memorizing the trying to memorize that system, which relied on a lot of memorization. All right, can't move my thing out of the way anymore. So let's go ahead and get the common names out of the way. And then after that, we've got our standard system with those prefixes we were talking about. But let's start with a discussion on common names. All right, so here's the ones I want you to know. We'll start with water. Most of these will have a name otherwise used in the system. Some of them will actually show up in some of the other systems, and don't be confused by it. It's not that difficult. H2O2, I want you to know, is hydrogen peroxide. All right. So this one is a real common example we give for just changing this understood 1 in H2O to a 2 and the changes it has. I'll use it as examples when we balance equations in chapters 3 and chapter 4, depending on which book you're in. And so you want to know, you want to have that one so you recognize it. You probably know this one, salt. Maybe you've heard it as table salt. All right, and that's just because the whole class of compounds for salt, we'll talk about this when we do acids, bases. The class of compounds is named after this compound, and that actually includes some other compounds that are salts, but they're not salt. Right, so that can be, so that's why a lot of people call this table salt. So we'll learn other names for this then. Let's do NH3. This is ammonia, and NH4 with a positive charge. This is one of our common polyatomic ions, but I'm going to put it in here so that we can see the difference. This is something, again, acid bases, and this chemistry shows up again in Fundamental Chemistry 2 and Gen Chem 2. You're going to be doing a lot with ammonia and ammonium, and this interaction between the two, it's key that you keep up with them. So the way I do it is NH4 positive has more stuff in it, has more hydrogens, right? And so it gets the longer name. It's hard to tell they're long because I had to write in a smaller script. Let's see, 1, 2, 3, 4, 5. Oh, let's get an even number here. Let's throw in SiO2, and we'll use that for sand, if I can spell sand. All right, so we'll use this abbreviation when we separate salt from sand, for instance, in one of our lab experiments. We'll be dealing with sand, so if you see me write SiO2, I want you knowing it's sand. So these are memorization. You'll have to memorize these. No way around it, but they're not overly difficult. So, okay, everybody pause, take a picture. Great, it's gone. All right. So going through these systems, the first thing I'm going to start with is the most basic case, and then I'm going to come back and deal with, so I can go through my PowerPoints if I want to, but so I'm going to just start off with the naming system, and I'll go through all the systems, and then I'm going to come back and tell you how to choose between them, because that's its own skill. So the first system then is our standard ionic. So this is used when we're in group 1, group 2, and aluminum. You can also look at this as the S block and aluminum. Now, it does not include hydrogen in group 1, so it's not usually used in this naming system. So typically we look at it in terms of a metal. So these are ionic compounds. So this is ions. If I'm looking at a periodic table, let me pull up one. So group 1, group 2 over here on the left-hand side, and these will be metals with some non-metals. In other words, I'm crossing my staircase, so I have a large difference in electronegativity. The things close to fluorine have a high electronegativity. That means they want the electrons more, and the ones that want them more get them. The things over here have close to cesium have a low electronegativity. So because of this, we have, when we combine, say, sodium and chlorine, that the sodium wants to lose an electron, the chlorine wants to gain one. And so we get a transfer of electrons. So if you see ionic, when we talk about bonding, we see a transfer of electrons. And so the one that is the non-metal or closest to fluorine, that will be our negative ion. That's also referred to as our anion. And the positive ion is called the cation, and it will be the metal in these cases. All right. And hey, okay, so we were talking about the ions, then I totally forgot to change scene. So let's record things a little bit, back things up. Boy, I can go for 20 minutes looking at the wrong thing, writing all kinds of stuff. So I was looking over here at these, and we were talking about our sodium and our chlorine, and trying to decide what things were positive, what things were negative. So I'm going to click over here, and I want to look at my negative ions. Those are the things close to fluorine. Those are my nonmetals. Those are called anions. I will use that term a lot. Positive charged ions are cations. And what's vital about this naming system is identifying which things will be cations and which things will be anions. All right. So our group 1 and group 2, these charges we can predict off the periodic table. So they follow the Octet Rule in these groups, so it makes life a little bit easier. Group 1, so here's my group, and here's the charge. Let's just make a little table. Group 1 will be a +1. Group 2 will be a +2. Aluminum will make a +3. Now, we could try and include boron, but it does some weird stuff, and we don't want to cross under the staircase. All right, and then I'm going to look over here at group 17, and it's going to make a -1. Now, group 18 doesn't react. It stays at 0 charge. It's not going to do anything. Group 16 then makes a -2. Group 15 likes to make a -3. Group 14, you would predict it would make a -4, but it usually doesn't make charges. All right. So here's my kind of run through for using the Octet Rule to make these predictions. Main thing I want to be able to do, though, is to predict if it's in group 1, 2, or if it's aluminum, it has only one possible charge. And that means that we're going to use this system, our standard system, and we know which one is going to be positive. And why that's so important is this system relies on you putting the positive ion is our first word, and then the negative ion's root, and an IDE suffix. So I'll use this language, suffix and prefix, a lot. Suffix is at the end, prefix is at the beginning, which pre is actually a prefix meaning at the beginning. What? It's in the, so I always thought that was interesting use of that language there. So let's look at a nice simple one, sodium and chlorine. So when naming these, you have to decide which one's positive and which one's negative. Sodium's in group 1, chlorine's in group 17. And so there's my positive and negative, and you have to make sure you do these steps. Do not assume that the positive is listed first. The positive has to be named first, but there's no such rule for the formula. And that's a trap that the books nowadays lay for you, because they cut and paste these formulas a lot. And so when we do this, make sure you figure out which one's positive, which one's negative. And as I go through all of our checklists, you'll see that we'll make that distinction by looking at the periodic table real quick. So I'm going to list my sodium and then my chlorine, and I need to drop this to the root. Now, the root is based off of sound, and we won't really be testing you on that, but I'll go through some of those for you, and then we take this and we make it IDE. So let me go through some of these on the periodic tables and show you what these become, so you hear the roots, because they can be a little confusing at first. All right. So looking over here, first off, hydrogen, if it has a negative charge, it would be hydride. Hydride. All right, not hydroxide, that's a polyatomic ion. So hydride is hydrogen with a negative charge. Fluorine becomes fluoride. Chlorine becomes chloride. Bromine would be bromide. Iodine becomes iodide. Oxygen is oxide. Sulfur becomes sulfide. All right. Selenium becomes selenide. Nitrogen is nitride. Phosphorus would be phosphide. Carbon is carbide. All right. So if we see those with that suffix, your main thing you're looking for is the IDE. So multiple choice, Not a problem. You'll be able to figure it out. Now, the big one, though, is hydrogen versus hydroxide. You really want to make sure you're careful on that. And we're going to see stuff like sulfate and sulfite. This IDE helps us a lot. All right, so this is based off of the atom, and then we put it, tells me it's negative. So when I see sodium chloride, I know the sodium is positive and the chlorine is negative. All right. So let's try another one here. Let's do that one I drew just kind of randomly a while ago, MgCl2. Mg is in group 2. It'll be a +2. I don't need anything other than the fact that it has to be a 2. I just need the fact that it's a positive. Chlorine is going to be a negative charge again. So again, this will be magnesium chloride. Let's do another one. Let's do KBr. Potassium. Oh, man, I hated spelling this. Dear old Dr. Milligan told me how to spell this. He said, you spell pot, you spell ass, you spell eum. Potassium. And this bromine becomes bromide. Now, you'll sometimes catch that I do so much work in symbols that I almost always make my H's with a capital, and then sometimes I randomly capitalize in the middle. Don't worry too much about that. A previous student told me that that was a sign of insanity, but we voted, and at the last vote, we're not insane. Oh, I mean, I'm not insane. All right, so this system's not too bad. Now, occasionally you get some tougher ones. OMG, there's a tough one. All right, so we're going to name this. You have to be careful. The magnesium has to come first. All right. Even if we see stuff like this is aluminum oxide. Notice I don't do anything with these subscripts. They're not involved in the name at all. So it doesn't matter which order they're in, and what matters is what charge will they have. So in this case, this is a magnesium with a +2 and an oxygen with a -2. I just care the fact that here's my positive. It has to come first. So that's our group 1, group 2, and aluminum. All right. So that system is pretty straightforward. I like that system. But what if it's not group 1, group 2? So I'm going to label this not group 1, group 2, and aluminum. In other words, this is my D block, the F blocks, my transition elements, right? And under the staircase, except aluminum. Now, the problem with these is many of these can have multiple charges. Not all of them, but we see stuff like iron can be a +2 and a +3. And so we have to be able to distinguish between these. It'll give us 2 different compounds, 2 different formulas, 2 different containers when I go into the stockroom. So if I tell someone, go get me some iron chloride, if they grab the wrong one, it could be quite dangerous. And so we want to be careful. If I say iron chloride, they don't know which one I was talking about. So we have to be more specific. And there are 2 systems. So the first is the stop system. And the second I'm going to call the ick and the us system. Okay. But both of which rely on us doing some algebra. And so they rely on us finding out what this charge will be. Because when I just see this formula written, if I just see some formula like this, I need to be able to figure out if it's a +2 or a +3. Now, some of you may be tempted to try and do what I call the reverse crisscross. And some of you have even been taught that. I have stomped pretty hard on that since I got to this campus, and we had it mostly solved. But if you know of somebody still teaching that way, you let me know. I'll send them a polite reminder that that doesn't always work. And the problem is it works sometimes, because when I did something like this, you might predict that this would be a 1. Well, my only options here are 2 and 3. How is that going to be a 1? And so this is a problem that we'll run into quite often. So no shortcuts here. We have to do the math. And so I often will state, when you're doing the stock and the ick and the us systems, you have, they're the newer system, and then the older system. You tell how much I love it. I don't even know who came up with it. All right. The way we do this, we summarize the math, but I'll ask you, hey, what do you have to do with these? You got to do the math. All right, so I'm going to summarize the math, and then we'll write out what it really means. So the math is summarized as the sum of the charges equals the total charge. And that's a good way of kind of reminding you of what it is, all right? But you need a little more specifics here. So the sum of the charges, I'm going to take each ion and with its charge. But what I'm actually going to do is I'm going to use these subscripts to tell me how many ions on it. So this one's telling me I've got 2 of these irons and 3 of these oxygens. Remember, if it's nothing there, that's an understood 1 down there. Now, the way we use this in would be the subscript. And I'm going to write it out because I'm running out of room here. Times its charge plus the subscript times charge equals my total charge. Now, you'll get set up for failure here if you remember this to be 0. The total charge you have to always check. 99.9% of the time in the lab, we work with it at 0. But if it's, and this is where many of those polyatomic ions get on that list, they have a total charge left. All right. So you can bet on the test will give you some that have a total charge. Where will the total charge be? It will be up here. It has to be given. Just like when I wrote this iron, I needed to say that was with a +2 and this had a +3. So the total charge would be up here. So if there's nothing there, that's an understood 0. All right. Now, sum of the charges. So let's do this Fe2O3. I've got 2 irons. I don't know its charge, so we're going to put in X. So 2 times X plus I've got 3 oxygens. And now I'm going to use the octet rule. In other words, I'm going to come find oxygen on my periodic table. So let's find it. So oxygen's over here in group 16. So you can think of this as 0, -1, -2. Or you can think it's got 6 valence electrons. It wants to gain 2. It wants to move forward 2 boxes to be to the nearest noble gas. So it wants to get to neon. When you move forward or when you gain electrons, the same result there, right? That gives us a negative charge because electrons have a negative charge. So this will be a -2 for my oxygen. And the total charge in this case is, in fact, 0. It's not always 0, so don't memorize this as being 0. It's whatever's indicated. And I'll try and drive that home to you, but we'll use this math a lot. This math is a game changer. Once you learn to do this math, instead of trying to do these shortcuts, all of a sudden this stuff's not too hard. You're probably going to internalize this math so much that you can do it in your head, and you're kind of thinking, well, I need this many of these charges to balance out so many of those charges. And so that's all this algebra is doing. It's doing that same concept. So 2x minus 6 equals 0. Algebra out of room. Oh, no. I guess I better stick to teaching chemistry. So x comes out to be a +3. All right. So this one, I know that this iron is a +3. Now, how I use that depends on these two systems. So let me go ahead. I'm Ooh. All right, sorry about that. So let me go ahead and get rid of everything. Get rid of this too. All right, so we're looking at this FeO now. So in this case, I've got 1 times X plus 1 times -2 equals, again, there's nothing up here, so this will be 0. So X minus 2 equals 0. X is equal to 2. This is my iron that's got a +2. So I've got Fe2O3, where this is a +3, and I've got FeO, where this is a +2. So 2 different compounds. So how we name these then depends on the system. So the stock system is actually quite nice. You take the charge and you put it in as Roman numerals. So we're going to put parentheses and we're going to put the charge. And we're going to add that as Roman numeral. All right. So in this case, I'll have iron 3 oxide. And notice I did the negative here just like I would with the other system. So this is the root with the negative. So we've got the positive has to come first. The charge on the positive is the only one that ever changes. Notice all these that are in my D block and under the staircase, those are all metals. They'll all be my positive ion. So then the other one would be iron, the FeO would be iron 2 oxide. And that's exactly how I would read this. Now, when I give this back to you on the test, it's really important, and we try to go backwards from this system. It's really important that you remember that this 2 is telling me the charge. That's going to come back to haunt us. So if it's in the parentheses, it's the charge. Drill that in your head. All right. Now, the ick and the us system is a little bit different. So the ick and the us system takes the Latin root of the positive. Oh, you already got to have the Latin. Oh, man. And then it's got the ick. Here's what I want you to know. The ick and the us suffixes. So these suffixes, the ick is for whichever one has the higher charge. Just the bigger number, right? And the us is for the lower charge. So this is a relative system. And so I remember it with an I in higher, I in there, lower has an O, so does OUS. All right. So the problem here is it depends on you knowing the possibility. So when I told you iron can be +2 and +3, the ick then would be my +3 and the us would be my +2. Then I'd have to know the Latin. The Latin for iron is ferrum. That's why that symbol is Fe. And so the Fe2O3, just write it up here, if I ever, yep. So this one is a +3. This is ferric oxide. And this one would be ferrous oxide. All right. So well, this system's a little more complicated than just sticking the name in the stuff, because you still got to do the same math to decide which one it is. But then you have to also know all the possibilities or look them up. So when this system was done, the only real people studying this were expected to know all the possibilities for every atom that every element that could have multiple choices. All right. Why wouldn't you memorize them all? All right. Clearly you should know all the Latin. So that's the problem with that system, because when I do something like copper, and I want to decide, is this cupric chloride or cuprous chloride, then when I do my math, 1 times X plus 2 times -1, because that's a halogen, right? Group 17. The total charge is 0. So X is going to come out to be 2. All right. When I do this math, this still doesn't tell me is it cupric or is it cuprous, because we can't just assume that the +2, because it was for iron was ferrous, that this would be cuprous. What we need is extra information. Now, I give this information to you on exams. All right. I will give you some kind of note. If I'm looking for a cupric or a cuprous, then I'll say note Cu can be +1 or +2. And now we can tell that this is the higher, so this is cupric chloride. Cupric chloride. It's always a fun one to try to spell. All right. What other name would that have besides cupric chloride? Well, CuCl2, that's also copper. We said it had a 2 charge. Chloride. So the cupric and cuprous, that system is still used mostly by old scientists and people in the medical field, which many of you want to go into. So I guess we'll keep learning it. I'll be glad when they quit using it, so we can let that become just an old forgotten naming system. All right, now we've got our polyatomic ions and how to handle those. And then we'll work on coming out of these ionic names. So polyatomic ions are a group of atoms that have a charge. And these atoms are, for the most part, held together with covalent bonds. And so we're looking at stuff like an oxygen bonded to a hydrogen. I'm going to go ahead and draw these little pairs. If you've been doing Lewis structures, you'd see this. All right. And the whole thing distributed over, it's picked up an extra charge. It has an extra electron. Instead of just having 7 valence electrons, it now has 8 valence electrons. So anytime we have this extra one, this is a polyatomic ion. And when we look it up on our list, OH minus is hydroxide. All right. So this is why I wanted formula, charge, and the name. Now, the key to polyatomic ions is they modify the 2 previous systems we've used. They modify our standard binary system, our group 1, group 2, and aluminum, or they modify the stock and the Ick system, okay? And so the key here is we do not change the ending to polyatomic ions. They just fit right into those systems. So when I come in and I do KOH, then I automatically know I have a polyatomic ion. And the reason is everything we're going to study is binary except the polyatomic ions. Now, polyatomic ion, remember, poly means many. Poly means many. So this is an ion, and you can catch all kinds of things here. So when I see 1, 2, 3 capital letters, I immediately know I have a polyatomic ion. It's going to be an ionic bond. But I have to identify what the polyatomic ion is. Is it KO? Is it OH? This is why having that list memorized really helps. I can see that this is a polyatomic ion. Now, when I'm naming this, then I have to still look at my potassium and figure out which system to use. So potassium's in group 1. I can get by with just calling this potassium because it will always have the same charge. It's my positive. Now, my hydroxide is the next word. And I don't have to change the ending. It's already "ide," so that's easy enough. Okay. Let's do... Oh, man, I got all kinds of stuff going on here. I've got a capital letter, another capital letter, another capital letter. I've got a polyatomic ion. When I look through my list, hopefully we figure out that this is a polyatomic ion right here. Okay. I've got, this is SO4. That's all one piece, and that is sulfate. It has a -2 charge. Now, my sodiums have a +1 charge. So that means my name on this needs to be sodium sulfate. The sodium has to come first. Sodium sulfate, though, make sure you don't change this. Don't put sodium sulfide, because that is something different. That is Na2S, where the sulfide is from sulfur. And then there's also a sulfite. So be careful. Be careful. Don't change the ending. Now, we can use polyatomic ions in all these systems. So we could do an FeNO3 2. All right. And when we do our math on this, got to remember this is one piece. And you'll notice I put my polyatomic ion in parentheses when I have more than one. So these understood ones and understood parentheses can be a problem. Don't be afraid to add them back in. There's nothing wrong with it. It's just a sign that you're kind of new around here, but it really does help. So add in this understood one here. Later on, you'll get used to adding in maybe even that one. But the key is this is one piece. And so this whole piece, I'll have to treat that I have two of these pieces. What this is saying is I have an Fe. We don't know its charge yet. We'll have to find it. I have an NO3 and another NO3. Now, if I didn't have the parentheses, I would have this 2 out here would be confusing. Even if there wasn't this 3 here, you might say that it doesn't distribute to the 2. Now, why did I not write N2O6? Because that loses this information that it's 2 of these. If I look on my list, I'm not going to find N2O6. All right. Fe with NO3. So I've got to do my math. 1 times X plus 2. Now, nitrate is my compound here, NO3, and it's got a -1 charge. The total charge out here is 0. So X is going to work out to be 2. So this is iron 2 nitrate. Had to get nitrate from the fact that it was NO3. All right. Now, if I knew that iron could be a +2 or a +3, then I could also call this ferrous nitrate. One of these two would be on there, all right? But the dangerous part where we run into trouble is so would iron nitrate. So would iron nitride, where we change this ending. Don't change that ending. So I like it when you get polyatomic ions. I really like it on the, once you learn the polyatomic ions, they make your life easier. So when we see something that's crazy looking like this, I've got polyatomic ions all over the place. And so what I really have is one of these and one of those. And I have to have done that memorization to know that this is ammonium and this is nitrate. Notice it's my positive. And nitrate. And so this is ammonium nitrate. That simple. Oh man. Oh, that bomb, the explosion in Beirut. There we go. That's what that was. So be mindful of your polyatomic ions, but to me they make life easier. So let's work on coming out of these ionic names. Let's look at something like let's do magnesium nitride. So we can tell immediately some things about this. The fact that it's nitride, you're going to have a hard time finding that on the periodic table. So first I'm going to recognize there's a nitrate, a nitrite. Those are my polyatomic ions, but nitride, that came from nitrogen. So I'm going to write that symbol. Here's my N. The symbol for magnesium is Mg. And then I'm going to find their charges. And so for this ionic compound like this, to find their charges, I'm going to come over here and I'm going to find the nitrogen. It's in group 15. It makes a -3 charge. I'll put a -3. So big up there. And then magnesium is over here in group 2, and so it's going to be a +2. So I'm going to come over here and I'm going to add a +2 for my magnesium. All right. The next step then is what we refer to as the crisscross. And what I'm going to do is I'm going to bring this charge, but I don't bring the sign, just the number, and I'm going to go bring those down to the subscripts. In other words, that 2 from up there comes down here, and the 3 from my nitrogen comes down here. Don't bring the negative sign. You can't have a negative number of atoms in the formula. All right, so here we go. I've got this formula, and then the last step is I'm looking for the smallest whole number ratio. Anything with ionic, we want the smallest whole number ratio. So we got to check our ratio. Our ratio is 3:2. Is there any way to reduce that by dividing them both by the same thing and still get whole numbers? Nope, that would be 2 and 1/2. So nope, can't do that. So we're going to keep that. This is my answer. Now, a lot of times you see me add on these charges as we're doing. You don't have to indicate those charges when you write the formula. Keep in mind, if we've got a polyatomic ion, we're going to need those parentheses. So let's get some more. All right. So let's do silver 1 chloride. Silver 1 chloride. So silver is Ag. Chlorine gives me C. Chlorine is in group 17. It'll be a -1. Silver, though, it's in the D block. We're not sure what its charge could be. We don't know if it can be a +1 or +2. There's nothing really here, but what's nice is this is the stock system, and I see these parentheses. That stock system tells me the charge. So a lot of people will put a 1 right here immediately, and that's a problem. That 1 is actually going right here. Now when I do my crisscross, I get Ag1, Cl1, and so we usually don't write the ones, they're just understood, but it wouldn't be wrong if you had them. Okay. Let's do a tougher one then. Columbic Hydroxide. I'm going to even tell you a note here. Pb can be +2 or +4. That kind of gives you a little bit of a hint. And so Columbic, when I see this, I might not even know which element that is. So you're going to have to be at least familiar enough with the Latin, or on a multiple choice thing, say, hey, Dr. J is not going to try and trick me on the Latin. And so that's Pb. We've got to know hydroxide. So you can bet that's on there as an option, Pb with an H. But it's not hydride. This is hydroxide, which is OH. So very common mistake. We know the hydroxide, this one, we memorize it, the name, the formula, and the charge. We need to know that that's a -1. We'll need that here. Now, Columbic, that should also be telling me the charge. What that's telling me is I can go to my options, and it's the it, so it's the higher. So this is a +4. So you might be tempted to write this PbOH4. But you're saying the wrong thing here. Here you're saying Pb and O and 4 H's. That's not what we want. We want 4 hydroxide. And so I'm going to put that in parentheses, which is saying PB with 4 OHs. So it includes the oxygen. All right. All right. So when I do this, I need to double check my ratio. And my ratio is 1 to 4. So it can't be reduced. All right. That step of reducing the ratio, that's why when I said we had to do the math instead of doing a reverse kind of crisscross when we were trying to do the naming, that's what that forgets and doesn't include. So let's do europium 3 sulfate. Europium 3 sulfate. Okay, so europium might take us a while to find it. We'll eventually find it. It's EU. Sulfate, got to have that memorized. You can look all day on the periodic table. You're never going to find it. So sulfate, SO4, it's got a -2 charge. And the charge of my europium is given here. It's a +3. And you can bet EU3 SO4 would be on there. And EU3S would be on there. All right, so now I do my crisscross. So when I do this crisscross, this 2 comes down here from here. This SO4, I'm going to put in parentheses a 3. All right. Now, a lot of times people will get a little confused and they'll try to reduce this ratio and they start looking at this 2 to this 4. This 4 is part of this piece. I have 3 of these pieces. So the ratio is 2 to 3. So this one's done. That can't be reduced down even. All right. So be careful about that on the polyatomic ions. But those aren't too bad. Practice them, practice them, practice them. So the last one system we want to deal with then is covalent. This is when we don't cross the staircase. All right. This is when they are sharing. All right. So we're not going to cross the staircase. So covalent stuff, these have the prefixes. And that's how you can identify them. They're the only ones that use prefixes. You'll get people that name these, name ionic things using those prefixes all the time. That's incorrect. It's not accepted. Now, some old naming systems actually did that, but those are no longer acceptable names. Okay, so I'm going to scroll down here and give us these rules for this. So let's look over here on these rules. It says we're going to name the elements in order we find them in the formula. And that's key because there is no positive ion. There is no negative ion. It's just whatever order we find them. And then we give the prefix at the beginning of the word to tell me how many of those atoms there are. So we're going to be using this. I like the page number didn't change in the newest edition. Only problem with the ebook, it's hard to find the page number. So table 3. That's 3.4. It's table 2.6 in Jinkin book. Okay. So here's our prefixes, and then the last parts where things get a little funky. The first element, if it has mono as its prefix, we get rid of it. We omit it, but only mono and only on the first element. And then the last element, we're going to drop it to its root and add IDE. Just like as if it was an anion, but just because it's got the second in the name. And then we're going to use the vowels. This is where things get in trouble here. This last one, it says final vowels in a prefix is dropped if the root name starts with a vowel. Now, so that one can be a little tough to see. So I've got some examples here. So here's carbon and oxygen. I've got monocarbon because it's one carbon, and monooxide because there's one oxygen. So we drop the mono for this monocarbon. We then would keep this mono, but monooxide sounds kind of funny. And so when we got two O's like that together, we sometimes drop the O. It's all based off of sound. So that won't usually be the difference. It just might be the difference someone giving you a funny look. So carbon monoxide is more difficult to say than carbon monoxide. So monoxide, we drop the O from this prefix. We get rid of this O here. All right, so now here I have monocarbon dioxide. We drop the mono from carbon. The dioxide, well, doxide sounds weird. Dioxide sounds a little better. So the I and the O, those two vowels we're okay with. So then here's SiO2, my sand. So silicon dioxide. Notice again we drop the mono. So these aren't too bad. What I like about these is it's really what you see is what you get. So I've got carbon. Hydrogen would be hydride. I have 4 carbons, so this is tetracarbon. 10 hydrides, that's decahydride. Make sure this isn't a mono. All right. Make sure I don't have 2 vowels next to each other. This makes it sound weird. And then we're done. All right. Tetracarbon decahydride. Now, careful. If I wrote this differently, it's got a different name. Now I have decahydrogen tetracarbide. And so that's what's nice about this system. You'll get different formulas from the different names, but when I go and look at these and pull them off the shelf, you'll see that they're the same. So covalent systems, really not too bad. And the nice thing about these, the use of the prefixes, is coming out of the system, you don't have to worry about doing any of this smallest whole number ratio or anything. So if they wrote to me trinitrogen hexaoxide, now you might say, is that hexoxide or hexaoxide? I'm gonna leave it as hexaoxide. So nitrogen, an N, oxide, so there's my O. I've got 3 nitrogens, 6 oxygens. I don't have to reduce this ratio. I don't have to do any of that extra work. It's 3 to 6, exactly as we see it. So the covalent system with these prefixes, really not too bad. Not too bad at all. All right. So coming into it and out of it, really not too bad. All right. So where are we at left? We got acids, naming. Oh, well, let's go ahead and learn how to name before I jump to acids. When we see some of these polyatomic ions, we were seeing nitrate and nitrite. All right, so nitrate was NO3 with a negative, and nitrite was NO2 with a negative. So these are polyatomic anions, and they have oxygens in them, and so that's another naming system that's still occasionally used, and they'll use it in Gen Chem. Matter of fact, we'll have it on that exam 1. And so the one that has the ite is our lower number of oxygen, and the one that has an 8 is the higher amount of oxygen. So it's a relative system. This is a relative system, kind of like the ich and the us system. And so the way that you have to be careful, it's not that it's a 3 and a 2, it's that it's more than this one. Now, some of them will have more than 2 options. So we also use prefixes along with the suffixes. So here's my suffixes. And the prefixes we use per and hypo. So hypo is less, and per then is going to be our more. And so the hypo goes will be less than the ite. All right, so maybe an NO. And so when we use these, then you've got, let's say there's 4 of them. That's the most common case where we are going to run into these. There's 4, then you're going to have 2 that end in ite and 2 that end in ate. So let's make a list here. Let's do BRO negative, BRO2 negative, BRO3 negative, and BRO4 negative. All right. So I've got 4 different polyatomic ions. So when I look on these, what you kind of want to key up is the middle 2. And those are my ites and my ates. And so we're going off of, here's increasing amount of oxygen. So the one that has the lower amount of oxygen, this is my ite. So this would be bromite. Keep in mind, bromide is just Br minus. All right. So this is bromite. And then I've got this one then that has more would be bromate. If it was chlorine, it'd be chlorate, right? So now I'm going to add prefixes to these 2 names. So the one that is less than the bromite is hypobromite. All right. And so I always think of there's a hypodermic where it goes under your skin, right? And hyper would be on top of your skin. So some medications are done in patches, and so they're put on top of your skin. All right, so hypobromite, so it's less than bromite. We need the one that's more than bromate, and so it's perbromate. Okay, so naming these systems, that might help you a little bit with your memorization. But this system then comes into play when we're naming acids. And so naming acids, when I was a student, I always kind of had trouble with it. But you're going to be just taking, so an acid's got an H plus, and it's going to be attached to, so this is a proton. We'll talk about later when we go in more detail on acids. But when it's attached to an anion, that makes an acid. All right. So if there's no oxygen, so I'm going to come over here, no oxygen in my anion. All right. Then it's just going to be hydro. And then that's my prefix. Oh, you guys can't see that. Let me make some more room over here. So hydro, that's my prefix, plus the anion root, and then plus an ic suffix, and then plus acid is a separate word. Okay, so it's always going to end in acid. So let's try way up here. I don't try not to erase this yet because we're going to use it. So HCl is a nice common acid. So this would be hydrochloric acid. Hydrochlorine. We'll drop the INE, right? And then it's going to be ic, and then the word acid. Hydrochloric acid. HBr would be hydrobromic acid. So we take the ide and becomes hydrobromic acid. So these aren't too bad. So Tn minus, that's cyanide, right? And so cyanide, if I put an H on it, hydrocyanic acid. All right. Let's see. Hydroiodic acid then. Good one. you can even memorize memorizing these is not too bad as long as you've got these polyatomic ions together. So when you're looking through your list of your polyatomic ions, let me find some of our list of polyatomic ions. Let's see. I'm trying to avoid anything with the 8s. So let's go ahead and jump into these when they have the 8s. So we get a different system use because we have these ites and the 8s and everything going on there, and so it becomes a little troublesome. So for instance, this is sulfate, and so I'm going to add enough H's to this to make it cancel out this -2. So I need to add 2 of these, and so I get this acid H2SO4. And so when I was a student, I had to memorize that. So I just remembered that this was sulfate, and so it becomes sulfuric acid, and we had to memorize it. But here's how we tell that that's going to be sulfuric acid. And so if it has an 8, then that becomes ic. So 8 goes to ic, and then you'll have your acid, and ite goes to us. So 8, remember, told me that it had more oxygen. So again, it's the higher amount of oxygen. Us would be the lower amount of oxygen, which was our ite. And then we also use the hypo and the, so it would be, you keep the hypo and then it becomes ic. And then we got the word acid. So let's add hydrogens to these and change the name. So let me switch over here, see if my blue will work. So I'm going to add, each of these has a -1, so I'm going to add an H in front of it. We'll get rid of each of those, add an H. We've now made them into acids. So this hypobromite becomes hypo, and ite has the less, so this is us, and then acid. And bromite, we drop this and we add OUS, and this is bromous acid. Okay. Now I've got bromate becomes ic and then acid. So bromic acid. And then this one will be per bromic acid. Okay. So when I did my sulfate, that became sulfuric acid, whereas sulfite will become sulfus acid or sulfurous. Yeah, sulfurous acid. I don't ever see that one. You use sulfuric acid all the time. Sulfurous acid. Well, that sounds even funny. But you could even then potentially have a hyposulfurous acid or a persulfuric acid. So these compounds be a little confusing. My advice, you write them out. And a lot of the times we'll give you the question and we'll remind you, hey, here's this one and here's this one. What would the one in the middle be? Or this. So just remember, it's all relative system. So it doesn't have to be 1, 2, 3, 4, but we are going to find the middle ones. And so this is my ite in my 8s, or my us in my ic. Okay, so higher amount is going to be ic, lower amount is going to be us. Higher amount is 8, lower amount is ite. Then we got hypo is less and per is more. All right. Woo, man. So that's down there. That's covering naming. We got it. I've got to edit these together. I've got to screw up when I was recording, right? And so I'll get those all edited. I'll get it all uploaded. And I will catch you on the next one. And I want you to study this stuff because naming is the things that give us trouble. Oh, hey, we should get a idea of how to tell which names to use. Man, let's just run through that checklist. It's really not hard. I ask these questions up here. I say, hey, is the compound ionic or is it covalent? How am I telling? I look at the periodic table. Then I say, hey, are there polyatomic ions? I actually check that first. So how am I telling if there's polyatomic ions? I count the capital letters. So I do that actually first. So when, let's say I see a compound here, CaF2, and then the last one I say, are the metals involved have multiple possible charges? So I'm just running through checklist. So I've got my CaF2, and I'm going to run through this checklist. And I put my finger over here on Ca, and I put my other finger over here on the F. All right, so Ca is way over here, and the F is over here. They're real far apart. I cross the staircase if I make a direct line between them. That tells me it's ionic. Ionic. I'm going to go ahead and label that down. There's only 2 capital letters. I'm going to put no polyatomic ions, no poly. While I still have my fingers here, I'm going to look at this and say, hey, calcium is over here in group 2. It's my positive. I want to know that. Calcium is my positive. And my positive ion, my calcium, is not down here, not under the staircase. It's not in the D block or the F block. It's in group 1, group 2, or aluminum. And so I don't have to use the stock system. I don't have to use the IC and the US system. I can just name this as a regular old ionic compound. And then the last thing I kind of ask myself is, CaF2, do I know a common name? And I don't. So no common name. No common name. And I saw this was in group 2 for my calcium. So those are the things I looked at by looking at the formula, looking at the periodic table. So when I do that, then I know this name is just calcium fluoride. And then I could use just the standard naming system. I didn't have to worry about any of these other things going on. So let's do another one. And so the hard part on these is talking yourself into the wrong system. So as soon as I see this, I've got 1, 2, 3 capital letters. I know that I've got a polyatomic ion. That tells me it's ionic. So if it's ionic, it will not have those prefixes. There's no common name for it. Then I find I'm not going to find the OH. I had to know that that went together is my polyatomic ion. And that's why I recommend memorizing that table. And then Na, I'm going to find it. It's in group 1. So I know that this is sodium hydroxide, and I don't need any Roman numerals or the IC and the US. It's just sodium hydroxide. When I do something like this, now I might immediately recognize, hey, this is the stock system. I can also look at this and tell it's ionic because there's no prefixes. Okay. So then let's see, maybe they gave me something like this, and I'm not quite sure how I want to name this. So I've got to find TB. That's terbium. That's down there in the F block. And then here's chlorine. So no polyatomic ions. This is a weird one. And so it's down in the F block. I don't know what charge it's going to have. Man, all I know is this thing gives me a green light if I run electricity through it. Ugh. All right. So I'm going to do my math. Then 1 times x plus 3 times minus 1. I knew this was my positive because I knew the chlorine. Well, first I knew it was over here as a metal, and the chlorine is a halogen. It's going to be a -1. So I knew that was a -1. So this will be terbium 2,3 chloride. And I had to use the stock system because I don't have enough information for the IC and the US system. I have no idea if this is turbic chloride or turbus chloride. because there's no note. Maybe if I wanted you to use that, I'd give you the note. Now be careful. Sometimes I'll give you the note, but we're still going to use the stock system. Those are interchangeable. But that's the checklist you kind of have to run through. So when you see something like this, you have to be careful, right? Because dialuminum trioxide will be on there, and it's wrong. Aluminum with a parentheses 2 is wrong. All right, why? Because we don't need it. This is just aluminum oxide, because aluminum is always a +3. Okay. So I usually wouldn't put one in with in the stock system to make it difficult, but I might do aluminum 2 oxide. This is a common one. Not only is it the wrong system, but how they did this, they took this 2 right here and they put it right there. Oh no, don't do that. Oh, I see people do that all the time. Oh man, here's one of the nastiest ones we ever tend to put on these. Let's do iron 2 sulfate. All right. So we're coming back out of the system. Iron 2 S and FeS and FeSO2 and Fe2SO4 and FeSO4 parentheses 2 and one more FeSO4. These are kind of options you get. So multiple choice doesn't make these easier. So we've got to identify which system we're using. We're using stock system, and this is the charge. So when I'm doing that, I've got to come in here and do my Fe, and I have to identify sulfate. And sulfide is with these, so it's not going to be that. So SO4 is sulfate. It has a -2. My charge here is a +2. So when I write this, be careful that you put this in the parentheses. And this 4 does not get reduced down. It's part of the piece. And so this comes down to FeSO4, and that's my right answer. All right. So you run through the checklist, kind of going in both directions, but put your fingers on the periodic table when you find these, all right? Find which one's positive, which one's negative. Is it ionic? Is it covalent? If they're right next to each other and they're both non-metals, it's a covalent system. Easy, okay? So learning the systems is not really the hard part. It just takes a little bit of practice. All this takes practice. And the hard part for most students is to remember to practice how to tell which system, all right? Because there's a lot kind of going on. You got to decide which one's positive. You're doing a lot of decisions before you even get started with the naming. So it'll be all right. It'll be all right. You guys can handle this. Once you get this down, then it opens the world to a whole new language. And all of a sudden, things stop sounding Greek. And they stop sounding chemist. And you can understand when they rattle off a chemical name at you at the end of some advertisement. Take this medication and it contains this and this and this, and you'll recognize some of these names. All right, we'll catch you on the next one.